Hi guys, welcome to Computerized Control. This is Lab 1 on Adaptive Cruise Control System. Today we are going to focus on the specification and design using pole position methods. So the objective is clear. So we want to specify, design and test the controller for the Adaptive Cruise Control System. And in particular, we are using pole position methods. You know that on future works we will use different methodologies. So the first recommendation is that you should prepare a report with all the steps that you do on these sessions. The first session is related with the step-by-step procedure, and this is, I have it here on the recommendation 2. You should take Guide Lab 01, where you have all the commands that you need for going through this procedure. And on the second session is about optimizing the controller, and so the second session is about optimizing this value. So let's start with the plant. So in the plant you have the main vehicle, and the vehicle has its speed and the control action, so directly at the engine. And then you have the disturbances. So you have the foregoing vehicle that will change the speed, you have the wind, and you have the road slope. And the objective is to control the distance from your vehicle and the foregoing vehicle. In this schematics, you have more details. So you know that you are actuating directly on the injection, and then through the engine, the acceleration of the vehicle, and the sensor that will detect the distance to the foregoing vehicle. And then this signal is fed back to the controller, and the controller knows the reference from the driver, and you have also the external disturbances, wind, slope, and traffic. And so, but this was pretty much what we have presented last week. So regarding modeling and linearization, after this process, this was the result we got last week. And here still depending on the value of the parameters. And these parameters, you have it on your guide. So these engine torque, the mass, the drag coefficient, and so on. So all these coefficients are well listed on your guide. So what you have to do is to start the script in MATLAB or Octave, and then step by step introducing all the parameters so you can compute the transfer function. And if you do this, you get the transfer function with this formula. So this formula, this transfer function, is the baseline for your work. So this is the starting point from where you will develop your controller. So first thing, you know that we should take some analysis on the dynamic behavior of this transfer function. So let's take a look first on this minus sign that we have here. So this minus sign derives from the fact that if you accelerate the main vehicle, the distance decreases. So the distance to the foregoing vehicle will decrease. So you have this inversion. So this is not very much important. So let's just put it aside for now. The other thing is that you should analyze the position of the poles from the transfer function. And from this position, you see that you have a pole in 0, and this pole in 0 means that you have a pole at the origin, so you have an integrator. And this integrator somehow is expected because you are controlling the position with the acceleration. So the question that arises is this plant asymptotically stable? You should know by now that it's not, because you have here the pole on the borderline between the stability and the unstable region. And so you know that your system will not be stable. Additionally, if you make a step, you'll see that your output signal will evolve in ramp, and you can also make a zoom around this region and see that you have the inertia. This is the initial inertia related with the second pole that you have there. So you have an integrator that provides the ramp, and you have the second pole that provides this inertia. Okay, but now we are not developing our controller in continuous time. We are going inside the computer. So inside the computer, you need to have a discretized model, a time discrete model. So we are going from S to Z domains. And to obtain the transfer function in the Z domain, we need to make the discretization process. And you know already that for that you need this continuous to discrete function from MATLAB. And this is the result you get. So you have here the transfer function, sampling period 0, 1. So this is pre-selected. You don't need to select this value. This is already at your guideline. And so this is the transfer function that you come up. these poles are 1 at z equal to 1. So is z equal to 1 now on the discrete time is the integrator, and you have the other second pole that corresponds to the second pole that you have on continuous time. But now you have also a 0 that you didn't have on continuous time, and you know by now that this is somehow normal to happen. So if you do the pole zero map of of fz, so the discrete time transfer function, you see that you have the two poles around z equal to 1, and you have the 0 there. And now the question arises again, is this plant now asymptotically stable? The conclusions that you had on the continuous time should be the same that you have on discrete time, because this is an exact discretization. So you see that stability region now is the borderline of this unit disk, and you have, so these are two poles, but you see that one pole is exactly on 1, the other one in 0.99. So the one that is on the borderline is this first one, which is the integrator, and you see that if you do a step, you will get the same response. So the initial inertia and then the evolution in ramp because of the integrator. Okay, so these were pretty much expected. So let's proceed to the next stage. The next stage is to design the controller. And for designing the controller, let's put our focus on the controller. The first thing is that you have to select the structure. So you have two inputs, the reference that comes from the driver and the output, the signal that comes from the sensor. And the first thing you do is to select the structure of subtracting the reference and the output, so you get an error. So your objective, the first objective, is to put this error to 0. And then you have the control law. And for the control law, you know that we want the control to be linear. So let's pick transfer function CZ, and this CZ has to be now developed. Okay, so at this point, we have a constraint. We will introduce a constraint. This is a common constraint while developing controllers, and we also want to introduce this constraint because this is an additional challenge to you. So you know that the computer that will run the controller will have synchronized sampling from reading the signal from the sensor, processing the signal, and then writing the signal to the actuator. This is, in this case, the injection system. And you have this synchronization done throughout this clock. So this clock signal will synchronize the reading, the processing, and the writing of the system. The problem is that if the processing time is much smaller than TS, so you can read, so this is in time, you can read the signal, you can process the signal, and you can write the signal, and you can say that, okay, the sum of these 3 times, which is this delta, is much less than TS. So TS is the sampling period from one sample to the next sample there. And so it's okay that I can still return the signal in UK because this delta is much less than TS, so things are running okay. And then we have this computer free time, and then we'll do this again and again and again. But what happens is that sometimes it's not possible to read and write in the same sampling instant. Why is that? It's because you read it, then you compute the control action, and when you're ready to write for the actuation, it's already too late, because the sums of these times is on the same order of magnitude of the sampling period. And this can happen because your computer is slow or your plant is very demanding with a high bandwidth, so you want the system to be fast. And if you want the system to be fast, maybe your computer is not up to the game. So at this point, it's too late for returning UK, because UK should be returned there, not in the middle between samples. And that's not okay. So this is not correct. So what is the solution? The solution is that we assume already one sample delay. So we assume that it's not possible to read and write on the same sampling instant. So what we do is we read, we compute the control action, but we introduce already the constraint that we are computing UK based on the k-1 information there. And then we hold the control action until the correct point and we write it there. So this, what we are writing here was the result of the previous processing. What we are writing here is the result of this processing. And that's okay. So, but we need to include this one sample delay. You know that one delay is about multiply by z to minus 1 in the z domain. This is a property of the z transform. So z minus 1 is the same as dividing by z. So our controller will have to include this delay there. So you know that C0 has the same number of poles and zeros, so there you don't have any constraint, and then there is where you want to put your focus. And then you have this additional element. So what I recommend is that because of this equivalence, dividing by z there or dividing by z there, because you have it on the same loop, it will be the same. Let's put the z to the plant and call it the plant, okay? So this fdz is our new plant. So we forgot that we have the delay. And by the end, when we are to test the controller, we put back the delay to the controller. But by doing this, now we are free to develop this C0 without any restriction. But instead of controlling this plant, we are going to control this one. So first step is to augment the plant with the delay. So you introduce here the transfer function of the delay with 1 divided by z, and then you make the series between the two blocks, and what you get is the two poles that you already had plus the additional one at the origin. And so if you make the pole 0 map, you have the additional pole at the origin representing the delay. So the plan to be controlled now is the same that you had previously, but now multiplying by z at the denominator. Okay, so next step is to specify the control system. So this is the H star, so this is what you want to achieve. Then to map this H star to H star Z, so the specification in the Z domain, where you're going to design the controller. So the designing the controller is your main challenge in this lab. And finally, test the controller with the simulator that you'll see later on. Okay, specification. And you know that you can include these restrictions as parameters of a second order model that we are going to call H star. Star in the sense that is what you want to target. So you know that overshoot is, this is a subject from the first semester. The overshoot is in close relationship with the damping factor D. So this factor D here that you are selecting will affect only the overshoot. You know that if you want an overshoot of only 5%, so this is our reference value, you want D equal to 0.7, and you know this value by now. Regarding rise time, and because D is already selected from the previous step, rise time allows you to select the natural frequency, omega n. And for instance, if you have 5% already selected, this means D equal to 0.7, and if you replace there, you have this formula. This means that if you want a rise time of just 1 second, and this is a value that is recommended for this work, you'll need a bandwidth, a natural frequency of 2.6 radians per second. So this is your the bandwidth that you are requiring for this system. So let's specify the pole location. So we are putting here a rise time of 1 second and 5% overshoot. So this means D equal to 0.7, and then you use the formula for rise time, and you get the H star transfer function. And this H star has this pole location, and if you draw it on the pole 0 map, you have these two stars representing what you want to target, what you want to achieve. And you see that this distance here is the natural frequency, 2.6 radians per second, and here you have 45 degrees, because when you have this 5% overshoot, D equal to 0.7, you know that this means 45 degrees on this on the angle of the poles. So this is what you want to target, but on the S domain. on the continuous time domain. Now you have to map these on the discrete time domain where you are going to design the controller. Okay, now you need to map the specification poles from the S domain to the Z domain where you are going to develop your controller. So there are two possibilities here. First is to use the formula that says the Z is equal to the exponential of STS. So that's one possibility. The second possibility with exactly the same result is, as you have already the HS star, you can compute HZ star by doing the continuous to discrete. So you can use this command in MATLAB with the zero order method that you used on the previous lab sessions to make the mapping from S to the Z domain. And then if you compute the poles, this is the pole location. When you put it on the pole zero map, you see it now that you have this, the target, the stars, the objective, your specification is in these positions. So when we are doing controller design and using pole position methods like with the root-locus, the first thing we need to test is, let's just try a proportional controller. And proportional controller means doing a root-locus of the transfer function of the plant directly. And if you do that, what you can see is that there is no possibility of developing a controller just using a proportional controller, because the poles immediately go to the unstable region. They do not get inside, they don't get near the stars that you want to target. So you need more complexity in your controller. So let's go. This is the main challenge that you have from this point on. Let's go to increase the controller complexity. And now, so this C0 that we have, let's put it as one pole and one zero. So same number of poles and zeros together with a K. And now your challenge is to find the best A, B, and K for developing this controller. So for that, I just put here some dummy values. I don't want to do the work for you, so I'm just putting here some dummy values that you'll see that the results will not be very good, but it will illustrate the step-by-step procedure that you need to do. So let's take these dummy values. We build up C0, the controller transfer function. We put it in series. Let's make the root-locus, and this is the result. Okay, we are not passing through the stars. You see that this pole and the zero, this is the position I've selected for this dummy controller. You see that the branches of the root-locus are not going through the stars at the moment, but you see that the inclusion of this pole and the zero had some impact in the sense that now the branches are inside the stable region. And by changing the position of this pole and the zero, I can change the way these branches move. So can you do better than this? I believe so. When you get your controller, after the development of your controller, you need to code it directly on your system. So, and this is the step-by-step. So you have a function in your controller. So this is an application that you are programming. This function is called controller. And now you have the several steps. First, you write on the digital to analog board the control action from the previous call. And now from this call, you read the signals from the sensor and from the reference. You compute the error, which is the difference. Finally, you have your control law, the UK. And then you have some updating on the buffers. So if you have this controller that you have developed with K, B, and A, and notice that now we have here the delay already back to the controller where it belongs. This is the difference equation that comes up from the transfer function, and this is what you develop directly on your system. So these parameters A, B, and K, they go directly on your code, and these are the ones that you should test. So the minute that you have your controller ready, you are ready for testing the controller. So let's put the controller inside the car. So we don't have a car, but we have this nice simulator. So in this simulator, you have the possibility of seeing the animation. In this animation screen, you can see how the simulation runs between these two vehicles. You have here the time, and you have the possibility of putting the simulation in fast forward mode, because this will run for 180 seconds. That's 3 minutes. So you're not using real time because this will be boring. So you can have the possibility of pressing this fast forward button and it will run faster than this. Additionally, you have the distance. So it will change the position of this car, but you can also check the value there, and the reference distance, so the desired value for the distance to the foregoing vehicle, the values of the speeds, the control action, so these will be accelerating here on this side or braking on this one, and some information about the wind direction and the intensity there and there. And finally, the key performance indicator that we'll speak about it later on. So when you press here the controller definition, you can input the parameters of your controller. So this is pre-prepared, and you see that we have already here the dummy values that I've used. So this is the transfer function with the dummy values and the difference equation. So these values go directly on their specific position. So what I ask you is that you interpret this table and see and compare directly with the difference equation, because this is very intuitive. After running the simulation, so you start the simulation, and by the end of the simulation, you'll get the final results. And these final results, you have the overall key performance indicator value, but you have two additional ones, one related with the control action and the second one related with the tracking error. So the key performance indicator is penalizing the error, the quadratic error, that is the difference between the reference and the output during the simulation for 180 seconds times 0.1 of the sampling period. And so your tracking error should be kept at a minimum. But additionally, because we don't want the controller to be very active, accelerating and braking all the time, we are also penalizing the control action. And we are penalizing by weighting this util. So this util is related with the difference between two consecutive actions. So this is not penalizing the absolute value. This is penalizing the difference between two consecutive values. So if you have a controller that is accelerating and braking, this will be very much penalized, and your controller will not have a good KPI. So the control action should be smooth. So the best controller is about the balance between this tracking error that should be kept at the minimum, but also the smoothness of your control action. After the simulation, you can analyze the results because you have these three files. The folder is folder data on your simulator, and you have one file related with the raw data, the other one with the script file that you can use for plotting the results, and the third with a report that you can send to me. So regarding the script file, it will produce these results. It will produce the plots where you can analyze the quality. For instance, you have here the distance to the preceding car and the reference values, and you can see the quality, but also here the control action. And if you have the control action very active, you know already that will also be penalized. And here the evolution of the key performance indicators. So by analyzing these, you can refine your controller. And this is already a result that it is possible to achieve. So you see that now the branches of the root-locus are passing through the stars. So this is my best design, so to say, but this for now is confidential. I'm expecting that you do your own development. And if you do a good job, you know that you can win the bar. So this is the final objective, to gain this chocolate bar that I have for you. So do not forget to have fun. See you next time. Bye-bye, guys.